Good day, everyone. This is the first recorded lecture in IE204-204L, Statistical Analysis for Industrial Engineering 1 Learning Module. This module has a duration of 6 hours. For the introduction, in all sorts of situations, we classify objects into sets of similar objects and count them. This procedure is the most basic motivation for learning the whole numbers and learning how to add and subtract them. This module introduces the basic language for talking about sets and sum notation, for setting out calculations so that counting problems such as this can be sorted out. This also discusses the scientific process involved in them, which includes counting techniques and probability. It is necessary to understand the basic concept of probability, which is most important to the study of statistics. As industrial engineers, it is important for us to be good in statistics. But first, we have to study the basic concepts under it, which lies in the concept of probability. For the objectives, after careful study of this module, you should be able to do the following. Number 1, describe the relations between sets, perform the set operations using proper notations, and be able to draw and interpret Venn diagrams of set relations and operations and use Venn diagrams to solve problems. Number 2, recognize when set theory is applicable to real-life situations, solve real-life problems, and communicate real-life problems and solutions to others. Number 3, understand and describe sample spaces and events for random experiments. Use permutations and combinations to count the number of outcomes in both an event and the sample space. And lastly, number 5, understand random variables. Before we proceed to the lesson proper, I want to show you a video about probability so that you have a prior knowledge about it. Okay, so please watch this video.
3 students were asked about the probability of passing in their mathematics paper. Let's understand their responses. The first student was very sad and said that the probability of his passing was low. The second one was really happy because he felt that the probability of his passing is very high. The third kid was a little confused. He says that his probability of passing is somewhere in between. So the probability just tells you how likely it is for an event to occur. Here, the event is passing the exam. In the first case, the likelihood of passing is not very likely. In the second case, the likelihood of passing is very likely. And here, the likelihood of passing is somewhere in between. But none of them are sure. They are just telling us what they feel and what is the most likely outcome. That's probability.
After watching that video, I hope that you gain some insights about our topic. So let's now go to lesson proper. The first topic is about set theory. 1.0 definition of terms. 1.1 set. A set is a collection of objects where the elements, symbolized by the Greek letter epsilon, usually have something in common. A set can be described by listing all of its elements for a finite set, writing a description of its elements or equation or function both for finite or infinite sets between curly brackets. Capital letters are usually used to denote a set. For example, let us define W as a set of counting numbers less than 10. So, we will write it as capital letter W is equal to open curly bracket And now we will list the counting numbers less than 10, which are 1, comma, 2, comma, 3, comma, up to 9. And then we will write a close curly bracket. Okay, so now this example is a finite set because it has a finite set of elements. So we can write 1, comma 2, comma 3, comma 4, comma 5 up to 9 are elements of set W. Next, let us define f, be an equation of the line. So f is equal to, open curly bracket, function of f of x, or the function of x is equal to 2x plus 5 for every x is an element of f, of the set f. 1.2 Subset. A subset is a collection of objects all belonging to a set. Its symbol is like this. It's like a letter C with an underline. Okay? So for example, let us define A as a set of odd numbers less than 10. So to annotate it, we will write capital letter A is equal to, open curly bracket, 1, comma 3, comma 5, comma 7, comma 9. And then we will write close curly bracket because 1, 3, 5, 7, 9 are a set of odd numbers less than 10. Next, let us define B as a set of prime numbers less than 10. Remember, a prime number is a number that can only be a product of itself and 1. So we will write B, capital letter B, or the set B is equal to, open curly bracket, 2, comma 3, comma 5, comma 7, close curly bracket. Because 2, 3, 5, 7 are prime numbers less than 10. Next, let us define C as a set of counting numbers less than 6. So we will write capital letter C is equal to, open curly bracket, 1, comma 2, comma 3, comma 4, comma 5, close curly bracket. Because 1, 2, 3, 4, 5 are counting numbers less than 6. Next, sets A, B, and C are subset of set W. And to write that we will write capital letter A, the subset sign, capital letter W. And for the next one, we'll write capital letter B, the subset sign, capital letter W. So next is capital letter C, subset, capital letter W. Because all elements of set A or set B or set C are in the elements of set W. That's why we call them as the subset of set W. Next, 1.3, universe or universal set that is symbolized by big letter W. A universe or universal set is a collection of objects of interest. It is also referred to as the totality of all objects under study or of interest. Uppercase of letter U is used to represent a universal set. For example, let us define big letter U as the set of real numbers. So, we can now say that the given set W is a subset of the universal set because it belongs to the set of real numbers, for it has elements that are real numbers. Next is the 1.4 empty or null set that is symbolized by a circle and a slash. So, a set with no elements. So an empty or a null set is a set with no elements. For example, let us define D as a set of counting numbers less than 10 that is divisible by 10. Since there are no counting numbers less than 10 that are divisible by 10, we can now write that set D, or capital letter D, is equal to open curly bracket, close curly bracket, meaning it is an empty set because there is no element inside it. Or we can simply write capital letter D is equal to the symbol of the null set or the empty set. Now let's go to 1.5 Venn diagram. A Venn diagram is a pictorial representation of sets and how they are related. Shapes such as rectangles and circles are used in this diagram. Okay, so a Venn diagram is used to represent sets. For example, draw the Venn diagram using the sets defined in the previous examples. As you can recall, we have a universal set, and we will write it outside the three circles, which are the given sets. So first, we will draw a big rectangle or a square to enclose those sets. So the first set is A. Set A is represented by this circle, the upper left circle. As you notice, the numbers or the elements inside set A are 9, 7, 1, 3, 5. That's why they are inside the circle or the set A. Next is the set B is represented by a circle in the upper right corner. As you can see, the numbers 7, 3, 5, 2 are inside set B because it is inside the circle of set B. Next is set C. It is represented by a circle in the lower part. As you notice, the numbers inside set C are its elements. Number 1, 3, 5, 2, and 4.
Now for 2.1, union. The union of two sets is a set containing all elements that are in either set. So when you say union, we are referring to all elements that are both in the given sets, or that can be seen in all given sets. So the symbol U is used to indicate a union. So remember this symbol. It is used to indicate a union. The following are the cardinality or the number of elements. When we talk about cardinality of a set, we are referring to the number of its elements. So number 1, n quantity A union B is equal to n quantity A plus n quantity B. Oh, there is a correction here. It is a typographical error of your module, okay? So this should be plus n quantity A intersection B for any set A and B. Why it should be a plus sign or addition sign? Because when we talk about union, we are including the sets in their intersection. So adding them should be the right way. So take note of that, okay? Next, n quantity A union B is equal to n quantity A plus n quantity B. This is for disjoint sets A and B, meaning this is for the given sets that are not what? That are not joined together or do not intersect with each other. So as you notice, the Venn diagram for them is this. The two sets, A and B, are not intersecting to each other. And we should shade the area within each set. Next, we go to another operation, which is intersection. So the intersection of two sets is a set containing elements in both sets. Okay, so the symbol, so remember the symbol, the inverted U, is used to indicate an intersection. The following Venn diagram shows the relationship of an intersection between sets A and B, or the quantity A inverted U B, or the intersection B. Okay, so to make a Venn diagram of it, we will shade the intersection between A and B because we are referring to the elements in their intersection. Next, two events A and B are mutually exclusive. When we say mutually exclusive, it is a term in statistics that that means that we are referring to two sets that are not joint, or in other words, they are disjoint. Okay? So if A intersection B is equal to a null set, because we are referring to their elements which are not present because they are disjoint. So there are no elements. That is if A and B have no elements in common. As you notice, the Venn diagram for it is like this. We will not shade any part because there is no intersection involved in here. Next is 2.3 complement. So another operation. The complement of a set contains all elements, not in the set, but still in the universe. So when we say complement, we are referring to the elements that are not in a given set, but inside a universe or a universal set. It is usually designated as this. So there are three options to designate a complement. First is a apostrophe, or a negative sign, or a proximity sign, a, or a with a bar. So any of those symbols will do. For its illustration of the Venn diagram, when we say the complement of set A, it should be like this. We will shade all the areas that are not involving the area of A, because we are referring to all the elements that are not inside set A. So 3.1, the identity laws. So this is the first law. So A union the null set is equal to the given set itself, which is A. Why? Because we are referring to the union of all the elements inside A and all the elements inside a null set. And there is no elements inside the null set. So we will just shade all the elements inside A. So it is equals to A. Okay? So next, A intersection U is equal to the set itself again. Why? Because all the elements inside set A belong to the universe, or to the set U, or the universe. So we will just shade all the elements inside A because it indicates all the intersection between the universe and A. Okay? So next, A union the universe is equal to the universe itself. Why? As I said earlier, all the elements of set A belongs to all the belongs to the elements of the universe. That's why we are going to shade everything here. Next is A intersection null set or empty set is equal to empty set because there is no intersection between them. There is no elements present. So it is equals to a null set. As you notice, we don't shade anything here. Next is the idempotent law. Idempotent law means that any set process or put into an operation with itself is equal to itself. Okay? So A union itself is equals to A. Then A intersection with itself, A is equal to itself again. Okay? So that is idempotent laws. Next is 3.3 complement laws. So here we will use a complement sign. So A union the complement of A is equal to the universe. Why? Because we are referring to the union of all elements inside A, that's why it is shaded, and all the elements that are not or that are outside A, which belongs to the universe or the universal set. So we will also shade all the elements outside A. So we will just simply shade everything. That's why it is equals to U or the universal set. Next is A intersection A complement is equal to null set. Why it is equal to null set? Because they are what? They are a complement. All the elements inside A do not intersect with all the elements outside A. That's why there is no intersection at all. There is no elements. So the resulting value is a null set. Next is the complement of the quantity A complement. So we have double complement here. It is just like negative times negative. So it will be what? A positive, which is equals to A. Okay, just simply shade the set A. Next is the commutative laws. So A intersection or union B is equal to B union A. Again, A union B is equal to B union A. Commutative law means that if you change the order, it is the same. Of the elements given, it is the same. That's why their Venn diagram looks the same. We just shade both elements that can be found in set A and B. Okay? So next is A intersection B is equal to B intersection A. So it is the same. So we will just shade their intersection. Next, 3.5, the Morgan's law. So Morgan's law is all about distributing the complement operation to each element and reversing the given operation inside a quantity. So first example is the complement of the quantity A union B. So is equal to, we will just distribute the complement to set A and the operation will be reversed. From union, it will be intersection. Complement B. So further, Venn diagram, you will notice that we will only shade all the elements outside set A and B because we are referring to the intersection of all elements that are not in set A and that are not in set B. So next example is the complement of the quantity A intersection B is equal to A complement, then from intersection it will become union B complement. So now we will just leave the intersection unshaded because we are referring to all the elements, to the union of all elements that are not in. So for its Venn diagram, we will just illustrate the opposite of the first given operation because the first given operation is A intersection B. So it should be shaded in their intersection, but we introduce a complement operation outside. So to get its complement, we will just get its reverse, which will result to this. All of the areas will be shade, while the area in their intersection will not. So it is just a reverse of the first operation. Okay? Next is associative laws. So A union the quantity B union C is equal to A union B union C. Meaning, if you interchange the parenthesis sign, it will be the same. So if you group B union C and you group A union B on the other side of the equation, it will be the same. That's why for the Venn diagram, all the shaded part are inside the given sets and also their intersection, because we are referring to the union here. Next is A intersection the quantity B intersection C is equal to the quantity A intersection B intersection C. So here it is also the same whether you group B intersection C or A intersection B. So for the Venn diagram, we just shade their intersection or the intersection of the three given sets. Next is 3.7 distributive laws. So A union the quantity B intersection C is equal to the quantity A union B intersection the quantity A union C. So here we will just distribute the operation and the given set outside the parentheses. So as you notice, we distribute A union to B, and then we distribute A union to C. Then it will be separated by the operation inside the parentheses, which is intersection. Okay, so for the Venn diagram, we will just shade the intersection of A union B and A union C. So why does the Venn diagram looks like this? So first, you imagine or you think in your mind that A union B should looks like a Venn diagram wherein A and B are shaded. Okay. The next quantity is A union C. So it should be A and C are shaded. So what are their intersection? So their intersections are these areas. Okay, the set A and the intersection or the intersection of the three sets. Okay, so you will imagine it. Okay, so one parenthesis to another before getting their intersection. Next is A intersection the quantity B union C is equal to the quantity or is equal to the union of the quantity A intersection B and the quantity A intersection C. Okay, so first you will think A intersection B. So what is the Venn diagram for A intersection B? So it should be shaded between A and B. And next, the intersection of A and C. So it should be shaded between A and C. Now we will join them. That's why its Venn diagram is like this. Now for the sample problems. A. For each case, shade the region representing the result of the indicated set operation. So A union B. Its Venn diagram can be like this. So we will just shade all the elements that belong to B to A and B. Okay, as you notice, it is the same for joint and disjoint. Okay, so number 2, A intersection B. Now we will just shade all the area between the intersection of set A and B. Okay, so as you notice, the first two examples have intersection, while the third one has no intersection, so it will be remained unshaded. Next, number 3, complement A or A complement. So we will just shade all the areas that are not in set A. Okay? Next number 4, the complement of the quantity A union B. So here, we will just distribute the complement sign. So we will now get the intersection of all the elements that are not in A and all the elements that are not in B. That's why for the Venn diagram, we shade all the elements outside set A and B. Next, number 5, we get the intersection of all the elements that are not in A because it is complement as well as with B, complement B. So, number 5 is just the same with number 4. Number 6. So now, we will distribute the complement. So, A complement and intersection now will become a union. So, A complement union B complement. So for the Venn diagram, we will just first think, okay? We'll just first think of all the elements that are not in A because it will become A complement. So we will think of them. And now we will think of all the elements that are not in B. So it should be outside B or the set B. Now we will just join them. Okay? That's why set B is shaded also because we will just join all the elements that are not in A. Okay, so it includes B and all the elements that are not in B. So this is its Venn diagram. Okay, next, number 7. So it is the same with number 6. Okay, because we just distribute the complement sign to each element and we just reverse the given operation. Okay, so it is the same. Now for letter B, which of the following have equal results? Use Venn diagram. So we will use a Venn diagram to show if they have equal results. So the intersection of the quantity A intersection B and C. Okay, so again, the quantity A intersection B intersection C is equal to A intersection the quantity B intersection C. So now, this illustrates a associative law. Why? Because we just rearrange them or we just group A, A intersection B in the first side of the equation and in the second side we just group B and C. So it is associative law. That's why their Venn diagram is the same. We will just shade the intersection of the tree. Next, A intersection the quantity B union C is equal to the union of the quantity A intersection B and the quantity A intersection C. So now for number 2, we have a distributive law because we just distribute the given set and its operation to all the sets inside the quantity. Okay, and now for the Venn diagram, it should be like this. Why? Because first we think of the intersection of A and B, so we shade its intersection. Next, we think of the intersection of A and C, so we shade their intersection. Now, because the operation between them is union, we will just shade their union. Okay? So number 3, A union the quantity B intersection C is equal to the union of the quantity A intersection B and the quantity A intersection C. Again, for the number 3, we have a distributive law because we just distribute the given element and the operation. Okay, inside all the sets inside the quantity. Okay, so now we will just we think of the first operation, which is A intersection B. So think of shading the intersection between A and B. Next, think of shading the intersection of A and C. Okay, so now make a union of them. So it should be shaded. It should be shaded like the area between A and B and the area between A and C. Okay, that's why it is not equal. Okay, so the first Venn diagram is not equal to the second Venn diagram because in the first Venn diagram all the areas in set A is shaded. Okay, but we should only shade all the intersection between A and B and A and C because we are pertaining to their union. So letter C, solve the following problems using set theory. Number 1, a survey on TV channel preferences shows 40 housewives prefer on the channel A. So you will notice that in the Venn diagram, 40 is inside A, but not inside in the intersection of A and B because it only prefers channel A. Next is 115 prefer only channel B. That's why in the Venn diagram, 115 is only inside set B. And 39 prefer both channels. That's why it is put here in their intersection of A and B because it prefer both channels. And 27 do not prefer either of the two channels, meaning this 27 here have no choice. They don't prefer either of the two channels. So A, for the first question, how many were included in the survey? So we will just shade everything in the Venn diagram and then we will just add all the figures. 40 plus 39 plus 115 plus 27 is equal to 221 respondents, right? Next, small letter B. How many prefer channel A? So, B, for the letter B, we are asked about those who prefer only channel A or who prefer at least channel A. Okay? So, we will just add 40 and 39 because uh, they are the group who prefer at least channel A. Okay? So 40 plus 39 is equal to 79 respondents. Next, letter C. How many prefer exactly one channel? So exactly one channel, we will just shade 40 and 115 because they are the groups who have prefer only exactly one channel. So 40 plus 115 is equal to 155 respondents. Next, letter D. How many prefer at least one channel? So at least one channel. So it means that we will shade set A and B and also their intersection because we are asked of at least one channel. Okay, so 40 prefers A, so it belongs to at least one channel. 115 prefers B, so it belongs to one channel. 39, it belongs to one channel also. So 40 plus 39 plus 115 is equal to 194 respondents. Next, number 2 problem. In a survey of 500 freshmen in the university, 200 are enrolled in Math 1, 180 are enrolled in History 1, 170 in Communications 1, 40 in Math 1 and History 1. That's why you will notice all those figures are inside its designated area. So 45 in History 1 and Communications 1, 50 in Math 1 and Communication 1, and 50 in all three courses. Because in here, uh, there are three sets given. Okay, so So 125 plus 25, 115 plus 35 belongs to M or Mat 1. That's why it is the total of 200. Okay? So for History 1, 25, 15, 30, 110, they all belong to History 1. And for the Communication 1, 35, 15, 30, 90, they all belong with Communication 1, Com 1. And the figure 70 here means that they are the students or freshmen that are not yet enrolled. Okay? So you have your summary here. So for the universal set, we will just add everything, all the numbers inside the square. So 500 students. Okay? For MHC, we just add all of the numbers that belong to them. Then for MHC, MNH, there are 40 students. Why? Because for math and history, so in their intersection, 25 plus 15 is equal to 40 students. Then for history and communication, in their intersection, we have 35 and 15. So it is, for H and C, 30 and 15. So it is 45 students. Next is for math and communication. So between them, we have 35 and 15. So 35 plus 15 is 50 students. Then for the intersection of math and history and communication, we have 15 students in their intersection. Okay? So how many students are enrolled in A? Math 1 only. Okay, so we will just shade the area inside M or the Math 1 only. So it is 125 students. Next, B, for Math 1 and History 1. So we'll just shade all the elements in their intersection, which is 25 and 15. Okay? Uh, so 25 plus 15, oh, we have a typo error here. So it should be what? It should be 40 students. Next, for Math 1 and History 1, but not Communication 1. So we will just get 25 students because it is in the intersection of Math 1 and History 1. Okay, but Communication 1 is not included. That's why the element 15 will not be included. So it is only 25 students. Okay. Next, letter D. Communication 1 or History 1. So we will shade all the elements that are both in Communication 1 and History 1. That's why when we add them all, it will be 305 students. Next, letter E, neither Communication 1 nor History 1. So we will shade all the elements that are not in Communication 1 and History 1. So when we add them, so 125 plus 70 is 195 students, right? So F, exactly 2 of the courses. So we will shade all of the elements that belongs to exactly 2 courses. So we will shade 35, 25, and 30. So when you add them, it is 90 students. Next, letter G, at least one of the courses. So we will shade all the elements inside M, H, and C because it is we are asked to shade at least one of the courses. So their sum is 430 students, right? Next, letter H, at most 2 of the courses. So we are asked to shade all at most 2 of the courses, meaning up to 2. Okay, so those who have only one pref, it is included. Okay, and those who have no preference, it is also included because we are asked at most 2, meaning 0 to 2, at most 2. Okay, so we don't include 15 because it has 3 preference. So their sum is 485 students. Next, letter I, any of the courses. So we will just shade all of the elements inside those courses. So for 130 students. Letter J, neither of the three courses. So it will be the 70 students because it has no preference. They have no preference. Next, letter K, not in Math 1 nor in Communication 1. So we will just shade all the elements that do not belong to Math 1 and Communication 1. So 110 and 70, total of 180 students. Next, letter L, not in both Math 1 and Communication 1. So we will just shade all the elements that are not uh, that don't belong to both Math 1 and Communication 1. Meaning, we will shade all the elements that do not belong to their intersection of Math 1 and Communication 1. So, the total is 460 students. Next, letter M, Communication 1 but not in Math 1. So, we will just shade all the elements inside Communication 1 but not the intersection between Communication 1 and Math 1. Okay, so 90 plus 30 is 120 students. Next, letter N, Math 1 and either Communication 1 or History 1. So, we will consider Math 1 and either Communication 1 or History 1. Meaning, we are referring to the intersection of Math 1 with Communication 1 or History 1. Okay, so we will just shade all its intersection with Communication and History 1. Okay, so 35, 15, and 25. Total of 75 students, right? Next, letter O, Math 1 and Communication 1, or Math 1 and History 1. So first, we will consider Math 1 and Communication 1. That's why we shaded their intersection. Next, the intersection of Math 1 and History 1. That's why we shaded their intersection. So we will just make a union of them. So it is the same, 75 students. Now, for the sample spaces and basic counting techniques, 1.0, random experiment. So what is a random experiment? It is an experiment that can result in different outcomes. So it has one or more different outcomes, even though it is repeated in the same manner every single time. So all the tests will be in the same manner. It always has a random component because it is a random experiment. It comes with a random component. So 2.0, characteristic of an experiment. So the experiment is such that it is impossible to state a particular outcome because we have to experiment first before stating an outcome. But we can define the set of all possible outcomes. So in an experiment, we can do our educated guesses or hypotheses. Okay, a set of possible outcomes. So number two, an experiment may be repeated indefinitely under unchanged condition. So we can repeat the experiment by our own decision. So it depends on us indefinitely, okay, with an unchanged condition. So number three, the outcomes of repeated experiments occur in a random fashion or by chance. Okay, that's why it is called a random experiment. Next, 3.0, sample space. The sample space S is the set of all possible outcomes. So we denote sample space with big letter or capital letter S as a set of possible outcomes of a single experiment. It depends on the objectives of the analysis. So next, 3.1, discrete. It is discrete random space if it consists of a finite or a countable infinite set of outcomes. So we should remember that if we have a countable, so if we can count the number of outcomes, it is discrete. Examples of these are numbers of pages of a book because we can count them, number of students enrolled in this class, and the number of correct answers in the quiz because we can count them all. Next, 3.2 is continuous. It is a continuous random space if it contains an interval. So, remember that. Either finite or infinite interval over real numbers. So there will be a pattern of interval between the numbers. So example of these are time, length, weight, volume, and area. Okay, so those are the examples of continuous because time continue to what? To go in and go, to go and go. Okay, as well as the weight and volume, it can go up or it can go lower. So next is 4.0, experiments and sample spaces. Experiments referred here to as those that are classified as statistical or random. A sample space is the set of all possible outcomes of the experiment. Events are any subset of the sample space delta. So we have a sign here, which is delta, Greek letter delta. So it denotes the sample space. So the notation epsilon for experiment. Okay, remember that. And delta, capital letter S for sample space. Okay, so again, so delta for the subset, okay, the subset of sample space. Y epsilon for the experiment. And capital letter S for the sample space. Okay, next, we go now to 5.0 counting techniques. 5.1 multiplication rule. If an application operation can be performed in n sub 1 ways, and if for each of these a second operation can be performed in n sub 2 ways, then the two can be performed in just multiplying them in n sub 1 multiplied by n sub 2 ways. Furthermore, if an operation can be performed in n sub 1 ways, and if for each of these a second operation can be performed in n sub 2 ways, and for each of these two a third operation can be performed in n sub 3 ways, and so on and so forth, then the sequence of k operations can be performed in n sub 1, n sub 2, n sub 3, so we will just multiply them up to n sub k ways. So such is known as the general multiplication rule. Okay, next is 5.2 permutation. So what is a permutation? Permutation. It is an arrangement of all part of a set of objects. Note that the order of n objects is significant. So here, its order, the order of the objects is important. So the following gives different permutation of objects. So number one, the number of permutations of n distinct objects is n factorial. So when you see an exclamation point, it means that it denotes a factorial. In your calculator, you can find that. Next, number two, the number of permutations of n distinct objects taken r at a time is, so now we have another element here, which is r at a time. So n, p for permutation, so n permutation r is equal to n factorial over the factorial of the quantity n minus r. Okay, so remember those equations or formulas. So number three, the number of permutations of n distinct objects arranged in a circle. So a distinct objects in a circle is the permutation of the quantity n minus 1. Okay? Or the factorial. Okay? So for the distinct objects arranged in a circle, the permutation of that is the factorial of the quantity n minus 1. So number 4, the number of permutations of n distinct things, of which n sub 1 are one of kind, n sub 2 are of a second kind, n sub k are of the kth kind, is where. So when you encounter a problem wherein uh, the given elements are of those different kinds, you can consider this uh, formula of permutation. Okay, so P, or the permutation, is equal to n factorial over n sub 1 factorial multiply by n sub 2 factorial multiply by until 2 n sub k factorial. Okay, so where n is equal to the summation of n sub I as I goes from 1 to k, because the value of I may increase, okay, from 1 to k. Next is for the combination. A combination is a special case of partitioning wherein R is equal to 2 cells. This defines the number of ways of selecting R objects from N without regard to order. So if the problem has no regard to order, it should use combination. The number of combinations of N distinct objects taken R at a time is, so this is the formula for combination. N combination R is equal to the matrix NR is equal to the factorial of n over r factorial multiplied by the factorial of the quantity n minus r. So remember those formula. Next is for the sample problems. We will now apply those formula in solving problems. So solve the following using counting techniques. How many permutations of 6 digits 1, 2, 3, 4, 5 are possible when repetition is allowed? So in number 1, we are asked to get the number of ways or the number of permutations that we can arrange these given elements 1, 2, 3, 4, 5 that can form 6 digits, and with repetition allowed. So for the solution, calculating permutations of the given digits means find the different numbers that are possible to be formed using digits. So we will find those ways and how many ways we can arrange them. So the condition that has been specified is that the repetition of digits is possible. So when you see a condition of repetition is allowed, this thing or this formula is what we will use. So the number of ways we can fill 6 places of any 5-digit number using 1, 2, 3, 4, 5 will be like this. So 5 permutation 5 multiplied by 5 permutation 5. So uh, as we count them, you notice that it is 6. Okay, 6, 5, because we are looking for 6 digits permutation. So 5, 1. So times 5, 2. Times 5, 3. Times 5, 4. Times 5, it's 5. Then times 5, 6. Okay? Because repetition is allowed. So you remember this formula if the problem says that repetition is allowed for permutations. Okay? So it is 15,625 ways. So number 2, in how many ways can the 18 members of a Boy Scout troop elect a president, a vice president, and a secretary, assuming that no member can hold more than one office? So here the solution is the problem requires position. So what are those positions? President 1, vice president 2, and secretary 3. So there are 3 positions. Okay? So those positions will be equals to uh, R in our formula. Okay, so and the condition that a member can hold 2 positions at a time, meaning there should be no repetition. Okay, so therefore we use the permutation without repetition. So what is the formula for that? So the formula for that is this. Okay, so as you notice, 18 is equal to the n. Okay, n in our formula, and p is permutation, and 3 is equal to r, the r in our formula. So is equal to 18 factorial over the factorial of the quantity 18 minus 3 equals 4,896 ways. Okay, next, number 3. How many words can be made by using the letters of the word simpleton, taken all at a time? So the solution is, this requires position and arrangement. Okay, so repetition of the letters is not allowed. Okay, so there are 9 different letters of the word simpleton. Okay, so the one letter is S is equal to 1 because there is only one S there, as well as I, M, P. So every letter in simpleton is equal to 1. Okay, there is no repeated letter in simpleton. Okay, so the cue here is taken all at a time, meaning there should be no repetition of the letters. Okay, so the formula for this is our formula of permutations for uh, different kinds of objects, because S is different for I, different for M, and different for uh, any letter inside simpleton. So we will use this formula. So N is equal to the sum of all different kinds of letters, which will add 1 plus 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 1 is equal to 9. Okay, so over 1 factorial multiplied by 1 factorial, since they are all 1, we will just multiply by 1 factorial, so 9 times. So it is equal to 362,880 words. Okay, next, number 4. In how many ways can the letters of the word pre-university be arranged? So the solution, this requires position and arrangements again. So repetition of letters is not allowed again. So there are 13 letters in the word pre-university. Okay, so 13 uh, distinct letters. Okay, so letter P is equal to 1 because there is only one P. Letter R is equal to 2 because there are two R's. E is equal to 2 because there are two E's, and so on and so forth. So we will use the previous formula again. So for N, it is the total, so 13 factorial over the number of each kind. So for P, it is 1, so 1 factorial multiplied by, for R, it is 2, so 2 factorial, up to Y. Okay, so it is equals to 778,377,600 ways. Okay, next, number 5. How many lines can you draw using 3 non-collinear, not in a single line, meaning of non-collinear, points A, B, and C on a plane? So the solution is you need 2 points to draw a line. Of course, we need 2 points. Okay, so for us to connect them to draw a line. So the order is not important. Of course, in drawing a line, the order is not important because we can start in either points. So line AB is the same as line BA. Yes, it is the same. The problem is to select 2 points out of 3 to draw different lines. Okay? So we will just select 2 points out of 3. Why? Because there are points A, B, and C, so there are 3 points. So if we proceed as we did with permutations, we get the following pairs of points to draw lines. Okay, so AB, AC, we can pair them, BA to BC, and CA to CB. Okay, so there is a problem. Line AB is the same as line BA. So it is the same. Okay. So same for lines AC and CA and BC and CB. So how do we deal with this problem? So the lines are AB, BC, and AC. So they are three distinct lines only. So in fact, uh, can draw three lines and not six. And that's because in this problem, the order of points A, B, and C is not important because uh, it is not stated in the problem that their order is important. Okay, so in other words, we have n is equal to 3 because there are n distinct lines. So n is equal to 3 different objects, and r is equal to 2 object to select at a time. Because to make a line, we will select 2 points. That's why our r is equal to 2. This is a combination problem. So combining two items, okay, out of 3. And it's written as follows. So we will just use the formula of combination. So 3, so 3 is equal to n in our formula. So 3 combination 2 and 2 is equal to r in our formula. Is equal to the matrix 3, 2 is equal to the factorial of 3 over 2 factorial multiply by the factorial of 3 minus 2. So it's equal to 3. So we can draw 3 lines. So 3 lines is the answer. Okay, number 6 problem. In Bulacan State University, students are to elect 6 representatives for Students' Council. There are 15 names on the ballot paper. Letter A. How many different 6 members council can be formed? Letter B. If the elected members of the council are to take up different responsibilities, then how many such councils can be formed? Letter C. There are 8 boys and 7 girls contesting the election. How many committees of 3 boys and 3 girls can be formed? So let's solve this problem or these questions one by one. So for letter A, the solution is this is a case of pure selection as ordering is not required here. Why? Why does ordering is not required here? Because it says that how many different 6 members counts can be formed. That's all. Okay, does not say order is required. Okay, so 6 members are to be selected from 15 candidates. So we will just use our formula for the combination. When you encounter a problem like this, combining uh, one group of element to another, you will use combination. So 15 is our n here. So combination 6, 6 is our r here because we will select six representatives out of 15. Okay? So it's equal to matrix 15, 6 is equal to the factorial of 15 over 6 factorial multiplied by the quantity 15 minus 6 factorial. So it is equal to 5,005 ways. Okay? Next is letter B. So the different responsibilities assigned to the council members brings in order. So because of the words different responsibilities means order is important here. Okay? Hence, discounting is a candidate for applying permutation formula. So because order is important, we will use permutation formula. So 6-member council can be formed from 15 candidates, okay, with different responsibilities. Okay, so 15 is our N, permutation 6 is our R, is equal to the factorial of 15 over the factorial of the quantity 15 minus 6. So it is equal to 3,603,600 ways, right? So letter C. Here, order is not required. Why? Why does order is not required in letter C? Because uh, it is not mentioned here. Okay? it only asks for how many committees of 3 boys and 3 girls can be formed. So order is not required. Okay, so but 3 questions are to answer in this sequence as follows. So we have three questions to answer here. So number 1 question: how many ways 3 boys can be chosen from 8 males candidate? Okay, so that's first. So we will use the combination. 3 boys from 8 male candidates can be chosen in 8 combination 3 ways. So we'll just use the combination formula. So it should be 56 ways. Okay, next. How many ways 3 girls from the can be chosen from 7 female candidates? Again, it is combination because we have an element of selection and a total population element. Okay, so when the problem involves selection from a total number of elements, we should use combination. So 3 girls from 7 female candidates can be chosen in 7 combination 3 ways. If you solve that, it will result to 35 ways. So last human numeral number 3, how many ways 3 boys and 3 girls chosen together? So a council consisting of 3 boys and 3 girls can be formed in, we will now just multiply those that we get from previous. Okay, so we will multiply 56 ways to 35 ways. That's why we get 1960 ways. Okay, next, for number 7, how many ways we can select 4 balls of same color from a basket that contains 6 black and 5 white balls? So solution: the 4 balls can be either 4 black or 4 white balls. Okay, so the number of ways to select 4 balls of the same color is, we will use combination again. Okay, because this problem also involves selecting some elements from a certain uh, n population or n number of elements. Okay, so we will just add them. Okay, so 6 combination 4 plus 5 combination 4, because in the first combination we have 6 black and the result can be 4 black or 4 balls. Okay, that's why we have for the first combination 6 black combination for uh, the results. Okay, plus 5 because we have 5 white balls, and of course combination 4 because there can be 4 white balls result. Okay, so we will just add them, so it is equal to 20 ways. Now let's go to number 8. A busy father asks his son to get books from his bookshelf that contains 15 business-related magazines and 4 religious books. How many ways are there that his son will get 6 business-related magazines and 2 religious books respectively? So here the problem doesn't require arrangement because it doesn't say so. So we'll use combination here, okay? Because it also involves selecting number of R objects from N. So the word A, the word and implies that there are 2 combinations to be multiplied, okay? Because the problem ask us how many ways are there that the son will get 6 business-related magazines, and because of the word and, we will multiply the combinations, 2 religious books respectively. So we will multiply in order to get correct number of ways. So first combination is 15 because there are 15 business related magazines. Combination 6 because his son can get 6 business related magazines. Multiply by 4 because there are 4 religious books. Combination 2 because his son can get 2 religious books. Okay, understand? So when we multiply those combination, we will get 30,030 ways. Okay. So number 9, a license plate has 2 letters and then 4 numbers in it. How many plates can be made without duplicating the letters and numbers? So there is no duplication or repetition. So for the solution, the number of ways 2 letters be arranged without duplication is 26 permutation 2 because we have 26 letters in the alphabet and we are to choose 2 letters only. So with the duplication, the formula, okay? So it is equal to 650 ways. Next, the first digit of the 4 number digits cannot be 0, okay? So we have 9 digits to choose from because it is 1 to 9. So we have permutation of 9, 9 permutation 1 because we are going to select the first digit. So it is equal to 9 ways. Next, for the remaining 3 digits, since there is no duplication, 9 digits are still available to be used. Okay, so we will not duplicate. That's why 9 digits are still available. So for 9 permutation 3 because there is a total of 4 numbers. Okay, we got the first number or the first digit. Now we will get the 3 remaining. Okay, so it is 3. 9 permutation 3. No duplication is equal to 504 ways. Okay, so you will just use the formula for the permutation with no duplication. So now we will just multiply all uh, the ways that we got. Okay, first is 26 permutation 2 multiplied by 9 permutation 1 multiplied by 9 permutation 3. Okay, so they are 650 multiplied by 9 multiplied by 504. It is equal to 2,948,400 plates. Okay, so number 10. There are 6 people lined up to get a bus. So letter A. In how many ways can 6 people be lined up to get on a bus without restriction? Without restriction means that repetition is allowed. So we will use permutation with repetition. So 6 permutation 6 is equal to 6 factorial, which is equal to 720 ways. Next, letter B. If 3 specific persons among 6 insist in following each other, how many ways are possible? So now, we will consider 3 specific persons as one person. Okay? So, consider this. So, 3 specific persons insist to follow each other. Okay? So, the first person is 1, 2, and 3. So, they are the first person. Okay? 1, 2, and 3. Next, the second person is 2, 3, and 4. Okay? So, they are the second person. Next is, so the third person is 3, 4, and 5. Okay? So they are the third person. Next, the fourth person, okay? Uh, it is 4, 5, and 6. So we have a total of 6 already. So we only get 4. Okay? So 4 arrangements. Okay? When 3 specific persons insist in following each other among 6, okay, we have 4 arrangements. Okay, you get it? That's why we got 4 permutation 4. So we have a general formula for that. Okay, so it will be n minus r. Okay, and plus 1. Okay, So 6 minus 3 is equal to 3 plus 1 is equal to 4. So we have 4 permutation 4. Okay, so that's the general formula. The quantity n minus r, okay, plus 1. So now we will multiply with the permutation of 3 because three specific persons insist on following each other. We will multiply it with the first permutation to that, 3 permutation 3. Okay? So 4 factorial multiplied by 3 factorial is equal to 144 ways. Next, letter C. If two specific persons among 6 refuse to follow each other, how many ways are possible? Okay? Now, in this problem, we are asked to find the ways if two specific persons refuse to follow each other. Okay? So first, we get the permutation of 6 permutation 6, because it is the total. Okay? Now, we will subtract the 5 permutation 5. Why 5? Because we have two specific person, okay, who refuse to follow each other. And why subtraction? Because it says refuse to follow each other. So we will subtract those two specific persons from 6, okay? And why we get 5? So likewise in letter B, though we will consider two specific persons as one group, okay? One group of person, okay? One group of persons. So the first group will be 1 and 2. So that's the first group. Next, the second group will be 2 and 3, okay? Then the third group will be 3 and 4, okay? Then the fourth group will be 4 and 5, okay? Then the fifth group will be 5 and 6. Okay, so there is a total of 5. Okay, that's why it is 5 permutation 5. Or you can use our general formula. So 6 minus 2 is equal to 4 plus 1 is equal to 5. So you get 5 permutation 5. Do you get it? Then we will multiply uh, the difference of 6 permutation 6 and 5 permutation 5 with the permutation of two specific persons who refuse to follow each other. Okay, so we get 720 minus the product of 120 and 2, which is 480 ways. Okay, do you get it? So here, because we will observe PEMDAS, we will we will first multiply before subtracting. Okay? So we will first multiply 120, negative 120 with positive 2. Okay? Before subtracting. Next, number 11. In a manufacturing operation, a part is produced by machining, polishing, and painting. If there are 3 machine tools, 4 polishing tools, and 3 painting tools, how many different routings consisting of machining, followed by polishing, and followed by painting for a part are possible? So here we will just simply multiply them all, because since there are 3 tools for machining, 4 for polishing, and 3 for painting, we will just use the general multiplication rule. 3 times 4 times 3 is equal to 36 ways. Next, number 12. So for number 12, there are 7 people sitting at a round table. So letter A. And how many ways can 7 people sit at a round table without restriction? Okay, so here we will use the permutation in a circle because it's a round table is present here. So the formula for that is without restriction, meaning repetition is allowed. Okay, so the factorial of the quantity n minus 1 is equal to the value of n here is 7 because there are 7 people. So 7 minus 1 is 6. So 6 factorial is 720 ways. Next, letter B. In how many ways can 7 people sit at a round table with certain 3 people side by side? So here we will get uh, the round the permutation of the 3 person. Okay, the 3 person, we will multiply them with what? The remaining 5 persons. So how do we get 5? Okay, again, we can use our general formula. So n minus 3 plus n minus r plus 1. Okay, so 7 minus 3 is equal to 4 plus 1 is 5. Okay, or you can use the grouping again. Okay, the grouping solution. But our general formula is more simpler. Okay, so we'll just minus 7 minus 3 is equal to 4 plus 1 is equal to 5. That is why our n here is 5. So we will just multiply the factorial of the quantity 5 minus 1 and the factorial of 3. So it is equal to 144 ways. Okay, next, with a certain 3 people not in a consecutive order. So here, when you say not in a consecutive order, it is the same, okay? The same with the previous problem, or the problem in number 10, okay? Uh, Meaning, 3 people is like refusing to follow each other, okay? That's why in our formula, we will first get the permutation of the total 7 people, okay? Then we will subtract, okay? We will subtract uh, the product of the permutation of the 3 people, and of course, uh, we will multiply it with the permutation that we get from uh, lessening 3 people from 7 by using our general formula. Okay, so n minus r, okay, plus 1. So 7 minus 3, 4 plus 1 equals to 5. Okay, so this question is the same with the previous one, which is refusing to follow each other. So it is the same with not in a consecutive order. Okay, do you get the pattern? Okay, so it is equal to 720 because it is the permutation of 7, the factorial of 7 minus 1, minus 144. Okay, so the answer is 576 ways. Next, we go to probability. So 1.0 probability distributions. 1.1 one-dimensional random variables. So if epsilon is an experiment having sample space delta, and capital letter X is a function which assigns a real number x of e to every outcome, then e is an element of delta. Next, then x of e is called a random variable. Okay? A random variable is a function that associates a real number with each element in the sample space. So here is the first example. Two balls are drawn in succession from an urn. What is an urn? It is like a jar containing 4 red balls and 3 black balls. What are the possible outcomes of the value x of the random variable capital letter X, where capital letter X is the number of red balls? So we are getting that possible outcomes. So let capital letter X be a random variable, which is the number of red balls drawn. So X is equal to 0 if the balls are drawn are black. Okay? Because we are asked to find the possible outcomes where x is the number of red balls. Okay, so if it is black, then x is equal to 0. Then if it is equals to 1, if the balls drawn are black, red, or red, black, it is equals to 1 because there is one red ball. So next, x sub 2, x is equal to 2 if the balls drawn are red, red, because there are two red. Okay? Now let's go to 1.2, types of random variables. 1.2.1, discrete random variables. If a sample space contains a finite number of possibilities or an ending sequence with as many elements as there are whole numbers, it is called a discrete sample space, meaning the elements have finite number possibilities. Okay? And the random variables defined over this space is called a discrete random variable or count data. So 1.2.2 continuous random variable. Of course, the opposite of discrete is continuous. So if a sample space contains an infinite number of possibilities, that's why it is continuous. It has infinite number of possibilities. Equal to the number of points on a line segment, it is called a continuous sample space. And a random variable defined over the space is called a continuous random variable, or what we call as measured data. Okay, so for the discrete random variables, we have count data. For the continuous random variable, we have measured data. Next, 2.0, probability distribution functions. 2.1, types of probability distribution. 2.1.1, discrete probability distribution. The function f of x is a probability function or a probability distribution of the discrete random variable capital letter X if for each possible small letter x. So here are its forms. Letter A, f of x is greater than or equal to 0. So it must be greater than or equal to 0. So letter B, the summation of f of x is equal to 1.0. Letter C, PR. What is PR? The probability. Okay? The probability of the random variable. Quantity, capital letter X is equal to A is equal to f of A, or the function of A. So next, the cumulative distribution f of x of a discrete random variable x with probability distribution f of x is given by f of x is equal to the probability of random variable x, capital letter X less than or equal to small letter x is equal to the summation of the function of t, as t goes from less than or equal to x. Okay? So for 2.1.2, continuous probability distribution, in dealing with continuous variables, f of x is called the density function. A probability density function, or PDF, is constructed so that the area under its curve bounded by x-axis is equal to 1.0. Okay, so that's the purpose of constructing it. When computed over the range of x, capital letter X, for which f of x is defined. The function f of x is a probability density function for the continuous random variable capital letter X, defined over the set of real numbers R. If, letter A, f of x is greater than or equal to 0. Letter B, so when you see a sign like this, it is read as the definite integral of f of x dx is equal to 1.0 from negative infinity to positive infinity. Okay, so letter C, the probability of the random variable quantity a less than or equal to x less than or equal to b is equal to the definite integral of f of x dx from a to b. So when you see a definite integral, it belongs to continuous probability distribution. So the cumulative distribution of f of x of a continuous random variable x with this density function of f of x is given. F of x is equal to the probability the random variable capital letter X less than or equal to small letter x is equal to the definite integral of f of t dt from negative infinity to positive x. Okay, so when you see a definite integral, it belongs to continuous probability distribution. Next, 2.2 characteristics of distribution. 2.2.1 the first moment about the origin or mean. So let capital letter X be a random variable with probability distribution f of x. So you notice that capital letter X is always a random variable. The mean or expected value is of capital letter X is for discrete is given by mu. Okay, mu is equal to the expected value of the random variable x is equal to the summation of x sub I f of x sub I, okay, from x, okay, as x goes to positive, okay. Next, for continuous, mu is equal to the expected value of the random variable x is equal to the definite. Again, when you see a definite integral, it belongs to continuous. It's equal to the definite integral of x of fx dx from uh, negative infinity to positive infinity. Okay? 2.2.2 second moment about the mean or variance. The variance, sigma squared, describes the spread or the dispersion of the probability distribution. So the positive square root of the variance, sigma, is called the standard deviation of the of x or the random variable with probability distribution f of x and mean mu. The variance of x is, so for discrete, sigma squared is equal to the expected value of the square of the quantity x minus mu is equal to the summation of the square of the quantity x sub I minus mu multiplied by f of x sub 1. So as x goes to positive, okay, is equal to expected value of x squared minus the square of mu. Okay, now for the continuous, sigma squared is equal to the expected value of the square of the quantity x minus mu is equal to the definite integral of the square of the quantity x minus mu multiplied by f of x dx from negative infinity to positive infinity is equal to, so this is equal, the expected value of uh, x squared minus mu squared. So as you notice, they are the same, but they differ in the definite integral. So continuous variable involves definite integral because we have interval here. So we use the definite integral. Next, 2.2.3. Mathematical expectation or the general form. Let x be a random variable again with probability distribution f of x. The expected value of a random variable g of x is, for discrete, the mu sub g of x is equal to the expected value of g of x is equal to the summation of g of x f of x. While in continuous, mu sub g of x is equal to the expected value of g of x is equal to the definite integral of g of x f of x dx from negative infinity to positive infinity. Okay, so for example, a random variable x representing the number of errors per line of software code has the following probability distribution. Okay, so we have uh, the random variables here 2, 3, 4, 5, 6. Then they have their corresponding probability distribution, which is f of x. Okay, so for 2 there is a 0.01, for 3 there is a 0.25 probability distribution, and for 6 there is 0.04 probability distribution. Okay, so find the mean of variance x. So the solution, uh, for the mean, we will use mu is equal to the expected value of x. So we will just multiply each random variable to its corresponding probability distribution, or f of x. Then we will add them all to get 4.11 for the mean. Next, for the variance, uh, so this is a discrete, okay guys, this is a discrete variable, okay, or discrete distribution. So variance, sigma squared is equal to the expected value of the square of the quantity x minus mu. So here we will get first the square of the difference, of each random variable and the value of mean that we got. Okay, we will get their uh, difference and we will square it, okay, one by one, and then we will multiply that to the corresponding probability distribution, or corresponding f of x value. So one by one, when we do that, we will get we shall add them all, okay, and we will get 0.7379 for the variance. So the variance describe the spread, okay, the variance describe the spread of the data from its mean. So let's go to 3.0 probability properties. If an experiment epsilon has a sample space delta and an event A is defined on delta, then the probability of the random variable A is a real number called the probability of event A. And the function probability of random variable has the following properties. 0 is less than or equal to the probability of random variable A less than or equal to 1 for each event A of delta, meaning the result should be 0 to 1. So next, number 2, probability of random variable delta is equal to 1.0. So for any finite number of k of mutually exclusive events defined on delta, the probability of the random variable summation of a sub I as I goes from 1 to k is equal to the summation of the probability of the random variable a sub I as I goes from 1 to k. Next, number 4. If A1 and A2 is the numerable sequence of mutually exclusive events, so they are mutually exclusive, defined on delta, then the probability of the random variable A1 union A2 union and so on and so forth is equal to the probability of A1 plus, okay, if they are mutually exclusive, it should be addition, plus probability of random variable 2 plus, and so on and so forth. Okay, so now let's go to 4.0, the source of probability. So 4.1, objective methods. 4.1.1, a posteriori method or past frequency. So posteriori, or the relative frequency of the past events, can be used as basis for probability measures. Of course, we will use past records to measure a probability of the future event. This could be obtained from a controlled experiment, as in a sample survey of a large finite population. Because in a survey, you can control your scope. Okay, so in this particular case, historical data helps in determining probability measure. If an equally likely event A occurs m times in a total of n trials, the observed probability, the probability of random variable A is equal to times A occurred over total number of trials, or m over n. Okay, so occurrence over trials. Next, 4.1.2, a priori method, theoretical distribution. Priori method makes use of the theoretical distribution of the aspect of experiment we are interested in. It uses an inherent quality of experiment. It is known that event A can occur in m ways, and a total of n equally likely ways is possible. The true probability, the probability random variable A is equal to the number of times of A to occur. So it is number of times over total number of ways of it, which is n. So the difference of the two is, the other is occurrence over trials, while the second is occurrence over number of ways. Next, 4.2, subjective method. Probability measures are determined through the judgment and experience. So here, there's no computation needed. It is judgment and experience that are used. So 5.0, types of probabilities. 5.1, simple probability. Assigned to a single event, probability A and probability, or the probability of random variable A and the probability of random variable B. 5.2, joint probability, assigned to events that should occur at the same time. Okay, if they occur at the same time, they are joint probability. So denoted by probability of random variable A intersection B, or the probability of random variable complement B intersection A. 5.3, marginal probability, assigned to subtotal probabilities, ignoring information about other events. Okay, so marginal refers to, or applied to, assigned to subtotal probabilities. So it is denoted as probability of random variable S is equal to the probability of random variable quantity S1 intersection L1 plus probability of random variable S2 intersection L2. Okay, so uh, when they are uh, inside a part that is at a subtotal of probabilities, we have to ignore the information about other events, meaning they are distinct in their own. So we will just add them. Okay. Next, 5.4, conditional probability assigned to conditional events. Probability A or B is equal to probability of intersection of A, probability of quantity A intersection B over probability of B. So we have those series of formulas that we will use. So 6.0, probability tree. A probability tree is a pictorial representation of conditional probabilities, which show all possible branches for each event. So this is like the Venn diagram uh, for the sets. Now, for the probability, we have the probability tree. Each branch is mutually exclusive, and completely exhaustive, meaning they are independent to each other. So the second stage is dependent on the first stage, since its probability differs for different first stage results. Okay? So, the sum of probabilities in each node must add up to 1 to get the probability of a specific outcome, meaning those nodes should share 1 or 100%. Multiply the probabilities of each branch from each other. So the symbols use point for node or the chance node, and the dash for branch or outcomes. So here is the example. If an experiment consisting of throwing a dice and tossing a coin determine the probability of each outcome, we draw the probability tree first. Okay, so the first node, notice here, and it comes into branches, okay, with the first probability 1 over 6, because 1 outcome over 6 outcome when you throw a dice. Okay, next, this has 2 probability if it is a head or a tail, because after throwing a die, you will throw what? You will toss a coin, which has 2 probability, head or tail. So 1/2. Okay, it's probability. So for the other one, it is the same. Probability number 2, they have all the same uh, probability, because you can only have one result out of 6 in a die, and you can have uh, one head or one tail in a coin. Okay, so they are the same. So we will just make a summary of them. For the first probability that it is head, 1 over 12. Why? Why we get 1 over 12? Because we just multiply 1 over 6 by 1 over 2, or 1/2. We get 1/12. Okay? The same for the probability 1 and tail. We just multiply the probability 1, which is 1/6, with probability tail 1/2. So we get 1 over 12. So it is the same with the other. Okay? Do you get it? We just multiply. Next, 7.0, the probability theorems. For each event A, probability random variable A is equal to 1 minus probability random variable A complement. Okay? So they are equal. Meaning, we will just subtract the probability that don't belong to random variable A with 1, because we are referring to, we are just basing from 0 to 1 of the results here. So we will just subtract them into 1. So 2, probability of, what is the symbol? The symbol is, it's a circle with a slash. Okay? So equals to 0. So meaning, the probability of the empty set, okay, or the null set, 0. Okay? So number 3, if events A and B are such that A is a subset of B, okay, then the probability of the random variable A is less than or equal to the probability of random variable B, because random variable A is just a subset of B. So it should be its probability should be less than, okay, less than to B. So number 4, if A and B are any of 2 events, okay, then number 5, there are any events, okay, A and B. Probability of random variable A union B is equal to the probability of random variable A plus probability of random variable B minus probability of the quantity of random variable A intersection B. Okay, however, if A and B are mutually exclusive, so you should remember this. If they are of any 2 events, meaning they are uh, they are with intersection, okay, you will use this formula. If they are mutually exclusive, meaning they don't have any intersection, because mutually exclusive means they are they don't have intersection. Okay, so you will use this another formula. Probability of random variable A union B is equal to probability of random variable A plus probability of random variable B. Okay. Next, for number 6, if A, B, and C are any three events, then now we have three. Okay, we have three given events here. In number 4 and 5, there are only two. So number 6, we have 6 and 7, we have three. So probability of random variable of the quantity A union B union C is equal to, okay, we will just put them one by one and add them. So probability of random variable A plus, because it is union, so we will add them. Probability of random variable B plus probability of random variable C minus, okay, we will just minus or subtract their intersection. Okay, we will pair them one by one. So A pair intersection with B, then probability of random variable A intersection with C, and B intersection C. So we will just pair them one by one, then we will add the intersection of all of them. Okay? Next, conditional probability. The conditional probability of B given A, denoted by probability of random variable B over A, is defined by, so this is the formula for the conditional probability. Next is for joint probability. If an experiment that the events A and B can both occur, then so A and B can both occur here. So probability of random variable A intersection B is equal to probability of random variable A. So these two dots means multiplication. Okay, so this is another typographical error here. Okay, so the two dots means multiplication. Take note of that. So probability of random variable B over A. We will just multiply them if they are joint probability. However, if A, B, and C are mutually exclusive, meaning they are separated, there is no intersection, the probability of A union B union C is equal to the probability of random variable A plus probability of random variable B. So we will just multiply them. We will just add them. Okay? We will just add them. Okay? If they are mutually exclusive. If they are joint probability, we will multiply them. Then if they are mutually exclusive, we will just add them or get their sum. Okay? The sum of their probability. Excuse me. So number 8, condition for independence. So two events A and B are considered independent events if and only if uh, probability of random variable B over A, so this is a conditional, okay, probability is equal to if probability of random variable B, then probability of random variable quantity A intersection B is equal to the probability of random variable B multiply, okay? The two dots again means multiply by probability of random variable A, okay? Then, as you notice, as we change the value in our uh, first variable in our condition, you notice that A is in the numerator now, while B is in the numerator in the first one. Okay, so when we switch it as our condition, uh, you will just switch the order. Okay, switch the order of the corresponding variables, but they will be multiplied again. Okay, two dots means multiplication. So number 9, if in an experiment that events A1, A2, A3 up to etc. can occur, then A1 intersection A2 intersection A3 intersection and so on and so forth is equal to the probability of A1, okay, multiply them. Okay, you will multiply because of the two dots. Probability of A2 over A1. Okay, so you notice that if they can occur, those intersection between them, you will just multiply uh, the first random variable A1 with the probability of the random variable A2 over A1. Okay, so that's the format. Then you will multiply the probability of the third random variable A3 over the intersection of A1 and A2. So you should memorize this format, okay, for the condition of such experiment that can occur. Okay, so 8.0 Bayes rule. It is also known as Bayes theorem. This is used for out of sequence events. It may allow one to calculate the probability of the cause given the effect. So if events A1, A2 up to AK constitute a partition of the sample space S where P of AI is not equal to 0, for I is equal to 1, 2 up to K, then for any event B in S such that P of B is not equal to 0, this is the formula. So P, or the probability of the quantity A over B is equal to P quantity A intersection B over P of B is equal to the probability of the quantity A intersection B over the summation of the probability A sub I intersection B as I goes from 1 to K. Then the probability of the quantity A over B is equal to the probability of quantity A multiplied by the probability of B over A over the summation of the probability of A sub I multiplied by the probability of B over A sub I as I goes from 1 to K. So that is the Bayes rule. Next, we go now to the sample problems. So for the first sample problem, a bag contains 4 red balls, 3 green balls, and 5 blue balls. What is the probability of A getting a red ball is? So first, the solution for probability of getting the red ball is equal to the number of red balls, which is 4, over the number of all the balls, which is 4 plus 3, 7, plus 5 is 12. So the probability of getting a red ball is 1/3. Okay? Letter B, getting a green ball. So the probability of getting a green ball is equal to the number of green balls, which is 3, over the number of balls, which is 12, the total number, which is 12. So the probability of getting a green ball is 1/4. Okay? So letter C, getting a blue ball. So the probability of getting a blue ball is equal to the number of blue balls, which is 5, over the number of balls, which is 12. So it is 5/12. Letter D, so the probability of not getting red. Okay, so we will just subtract the probability of not getting red from 1. So it is equals to 1 minus the probability of getting red. So 1 is equal to the number of red balls, which is 4, over the number of balls, which is 12. So 1 minus 4 over 3 is equal to 8 over 12, or 2/3. Okay? Next, number 2. In dealing a hand of 5 cards from standard deck, what is the possibility they are all spades? So we will get the probability or the possibility that we will get all spades. Okay, when we draw 5 cards from a standard deck. So to get the probability that we draw 5 spades, so the number of spades in a deck is 13. Okay, we will count the number of spades in a deck. So it is equal to 13. And the total number of cards in a deck is 52. So we will just divide them. 13 over 52 is equal to 1/4. So that is the probability of getting or drawing 5 spades. Okay. Next, number 3. If in 2 throw of dice, so we have 2 throws of dice, 6 always come up. What's the probability in getting 6 in third throw? Okay, so we throw the throw a dice, throw throw the dice twice, and now we will going to get the probability for the third throw. So solution: no matter how many times you throw a dice, okay, the probability of getting 6, it does not change. So it is true, okay, that it does not change. It is always 1/6. Each throw of a dice is independent of each throw. So the probability is 1/6. Okay. So number 4, a dice is thrown twice. What is the probability that the sum is divisible by 5? Okay, so for the solution, if a dice is thrown twice, this matrix is applicable. So we have a matrix here. Count the backs in the sum in which the sum is divisible by 5. Okay, so for the solution, we can use this matrix. We just put all the results 1, 2, 3, 4, 5, 6 to the uh, columns into the rows. Then we just add them. 1 plus 1 is equal to 2, 1 plus 2 is equal to 3, up to 6 plus 6 is equal to 12. Now, we will just select all results or all sum that are divisible by 5. So, we count them. 4 plus 1 is 5, okay, so that is 1. So, 3 plus 2 is 5, that is 1. Oh, we have 2, so 1, 2, 3, 4, 5, 6, 7. So there are 7 results that are divisible by 5. So now, after we got that, we will now get the probability that the sum is divisible by 5. So the number of events, okay, it is 7 because there are 7 uh, there are 7 sums that are divisible by 5. So over total number of outcomes. Why? Because uh, 6 times 6 is equal to 36. We have outcomes is equal to total number of outcomes is equal to 36. So the probability is 7/36. Number 5. If a pair of dice is tossed, what is the probability that the sum is either 5 or 6? Solution: if a dice is thrown twice, the matrix is applicable. Count the box in which the sum is either 5 or 6. So it is also applicable if the dice is thrown twice, the matrix. So again, we will just use the matrix and find out those uh, that yields the sum of 5 and 6 and count them. So to count them, they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9, okay, results which yields to a sum of either 5 or 6. So the number of events is 9 over the number of outcomes, which is 36. Okay, so lowest term, 1/4 is the probability. Next, number 6, a coin is tossed 3 times. Okay, so what is the probability of getting 3 heads? Okay, first, we get the probability of 3 heads is equal to the probability of head 1, head 2, and head 3. Okay, so we will just multiply them, the probability of first, second, and the third. So it is equal to 1/2 multiplied by 1/2, because there's a probability of 1/2 that we get head. Okay, head, because there are only two results, tail and head. So we multiplied them by 3 times, because we will toss the coin 3 times. So the result is 1/8, or 1/8. Next, 7. What is the probability that 7 people can sit with a certain 3 people not in a consecutive order? So the solution is the total number of ways 7 people can sit. Okay, back in the permutation. 7 permutation 7 is equal to 7 factorial 5,040 ways. So the number of ways 3 people sit in a consecutive order is, okay, remember our general formula for that. We will now get the factorial of 7 minus 3 is equal to 4 plus 1, 5. That's why we have 5 factorial. Okay, remember that formula. Multiply by the factorial of 3 is equal to 720 ways. Next, so to get the probability of 3 people not in a consecutive order, we will just subtract, okay? Subtract the probability of 3 people in a consecutive order to 1. So it is equal to 1 minus 720 ways over 5,040 ways. So it is equal to 6/7. So that is the answer, the probability. So the cue here is when you see the word not, okay, not in a consecutive order, not in the arrangement, meaning you will subtract the probability to one, from 1, okay? So number 8, a card is drawn at a random from a deck. What is the probability that the card is either an ace or spade? So first, we know that the total numbers of cards in a deck is 52. And we should know that the number of spade in a deck is 13. And we should also know that the number of ace in the deck is 4. So the probability of selecting a spade and an ace from the deck is equal to the probability of the quantity intersection of S intersection A is equal to 1/52. Okay, because uh, we only have one selection. Okay, if you draw once, so it is equal to 1/52, because you will draw one, okay, once, so 1/52. Next, the probability that the card is an ace is, okay, so the number of ace is 4/52, 52, the number of cards in a deck. The next, the probability that the card is a spade is equal to 13/52, because there are 13 spade in a deck, and the total is 52/52. So now the probability that we get ace or spade is equal to the probability of the quantity A union S is equal to probability A plus probability S minus probability of the quantity A intersection A. So you notice that this notation belongs to the probability theorem. Okay, so the value for probability A is equal to 4/52 plus 13/52. It is the value of probability S minus the probability of P quantity S intersection A, which is 1/52. Is equal to 16/52 is equal to 4/13. So they are not mutually exclusive. Okay? That's why we have a subtraction here. Okay? We will subtract the probability of the intersection S of S intersection A. Okay? Next, number 9. A toy manufactured by a company consists of two parts, A and B. In the process of manufacturing part A, 92 out of 100 are likely to be non-defective. It is for part A, okay? Then similarly, 89 out of 100 for part B. It is also non-defective. So number 9, a toy manufactured by a company consists of two parts, A and B. In the process of manufacturing of part A, 92 out of 100 are likely to be non-defective. Similarly, 89 out of 100 of part B is likely to be non-defective. What is the probability that the toy selected at random is non-defective? So, for the solution, let A denote the event that part A is non-defective and B denote the event that part B is non-defective. So, since the selected toy has to be non-defective, both parts must be non-defective. So, first we will get the probability of part A, that is non-defective. It is 92 over 100. And for part B, part B is non-defective, 89 over 100. So we will use those probabilities to solve the probability that the selected toy is not defective. Okay? Because when we select a toy, it can we can select or it can result to part A or part B. So they are joint probability. So they can occur at once. So probability A will be multiplied. So uh, remember that if probabilities can occur at once, okay, they will be multiplied. So probability A multiplied by probability B is equal to 92 over 100 multiply 89 over 100, which is equal to 0.8188 or 0.8188. So that is the probability of selecting a toy that is not defective. Next, number 10. A bag contains 12 red and 10 blue balls. Two balls are drawn at random from the bag without replacement. Find the probability that both of them are red. So solution. So the total of red balls is 12 while blue balls is 10. The total number of balls is, so we will just add them. 12 plus 10 is equal to 22 balls. So the probability that the first ball is red is 12 over 22. Okay? Since this is without replacement, okay, we will not repeat, okay, the other probabilities by getting the probability of the second ball drawn. Okay, so we will just subtract 1 from 12 because it is the second draw. Okay, so it will be 11 over 21, and we will also minus 1 from 22 because it is a second draw. Okay, so remember that when it is said that there is no replacement, you should minus 1 from the given number of an object and from the total number of object. Okay, so it is 11 over 21. So they are joint probability again. So we can uh, we can get them at a time. Okay, so once at a time. So the probability of both red is equal to 12 over 22 multiply. Okay, so we will multiply them. 11 over 21. So the result is 2 over 7. Number 11. Two math workshops were organized by the math club of the school. The first workshop was attended by 40% of high school students. But both the workshops were attended by 25% of high school students. What percent of those who attended the first workshop also took part in the second? Okay, so the solution is the first workshop was attended by 40% of the high school students. Then both the workshops were attended by 25% of high school students. So the probability that that attended the second over probability of the first, because we are getting the percent of those who attended the first workshop, okay, who also took in the second. That's why we will get the quotient of the probability of who attended both, which is 25, then probability of the first, which is 0.40. So we will just divide the probability of the attended they attended both 0.25 by the probability they attended the first. Okay, so by dividing that, because we are getting percent, that's why we divide here. Okay, we get 0.625 or 62.5%. So we will convert it to percent because it is asked in the it is being asked in the problem. Then number 12, the analysis of shafts for a compressor is summarized by conformance to specifications. So what are shafts? Shafts are metal handles, okay? And a compressor can be an air compressor or other compressor, meaning a compressor is a machine who exerts force, okay? Next, so this is the table that summarizes the data. So this for the surface finish conforms, those shafts who conforms to surface finish, if they conform, they have the total of 345, and if they don't conform, they have 12. And for the roundness conforms, those shafts who conforms in the roundness specification, if there are 35, 345 and 12, while those who don't conform are 5 and 8. Okay, so you see that there is an intersection between the specification. Okay, so letter A, if a shop is selected at random, what is the probability that the shop conforms to surface finish requirements? So for letter A, we are asked by getting only the probability that the shop conforms to surface finish. Okay, that's why we only get 350. Okay, 350. Why? Because under surface finish conforms, under yes, we have 345 and 5. So 345 plus 5, which is 350. So over 370, because it is the total number of shaft. So the probability is 35 over 37. Next, letter B. What is the probability that the selected shaft conforms to both surface finish and roundness requirements? So we will find both conformance. Okay, so probability that conforms to surface finish and roundness, meaning the intersection of them. So it is 345. Why? Because under surface finish, uh, the number of shafts that conforms are 345, and under roundness, the number of shafts conforms is also 35. Okay, so the intersection is what we are getting here. So 345 over, again, over 370 because it is the total number of shafts. So that is the answer already. Uh, you cannot make it into lowest term. Okay, so letter C. What is the probability that the selected shaft conforms to surface finish requirements or to roundness requirements? Or means either of the two. Okay, so for letter C, we have this. The probability that of the union of surface finish union roundness is equal to the probability of surface finish plus probability of roundness minus the probability of surface finish intersection roundness. Okay, so now we know the probability of surface finish, which we get in letter A, is 35 over or 350 over 370. So you will just substitute uh, the answer not in the lowest term, okay? We will just lowest term in the final answer, okay? So plus the probability of roundness is 300 what 357. How do we get that? So under roundness, under yes, the total is 357. Okay, that's why it is 357 over 370 because it is the total number of shops minus, so the intersection now of surface finish and R. So we got that in letter B. So we just copy it, 345 over 370. So adding and subtracting, we have 362 over 370. So we can make it lowest term. So 181 over 185 is the answer. Okay? So guys, you should remember when you see the word or, okay? Meaning you opt or you have to use this probability theorem, okay? Theorem notation. Okay, so letter D. What is the probability that the selected shop either conforms to surface finish requirements or does not? Oh, we have here a condition which does not conform to roundness requirements. So we will get the complement. Okay, guys? The word does not means complement. So for letter D, as you notice, we have a complement here. So the probability of surface finish SF union R complement because it says does not is equal to the probability of SF plus probability of R complement minus the probability of SF intersection R complement. Okay, so you should uh, be familiar with these probability theorems. Okay, and how you will use it in a problem. So the value of probability SF we got in letter A. So we just copy it. And now how do we get the probability of the complement R or the complement roundness? So we will get those that that do not conform in the roundness, which is of total 13. That is why there is a 13 here over 370. Okay, so minus the probability of the intersection SF and R complement. So how do we get that? Okay, so we will get the the elements that intersect in the surface finish conformance, which is yes, and in the roundness conformance, which is no. So their intersection is 5. Okay, that's why we select 5. You get that? Over 370 because it is the total number of elements. So adding them and subtracting them, we have 358 over 370, which is equal to 179 over 185. Okay, do you get that? Okay, so number 13. Suppose that the 4 inspectors at a film factory are supposed to stamp the expiration date on each package of film at the end of the assembly line. John, who stamps 20% of the packages, fails to stamp the expiration date once in every 200 packages. So that's our first data. Okay? So Tom, who stamps 60% of the packages, fails to stamp the expiration date once in every 100 packages. Okay? Next, Frank, who stamps 15% of the packages, fails to stamp the expiration date once in every 90 packages. And Pat, who stamps 5% of the packages, fails to stamp the expiration date once in every 200 packages. If a customer complains that her package of film does not show the expiration date, what is the probability that it is inspected by John? So this is Bayes' theorem, okay? So first, we will write all the given data that we will use uh, in our solution, okay? So the probability that John stamps, okay, 20% of the packages is equal to 20%. So the probability that John fails to stamp the packages is 1 over 200. Then the probability that Tom stamps is 60% of the packages. Then the probability that Tom fails to stamp the packages is 1 over 100. Then the probability of Frank stamps is 15% of the packages. And the probability that Frank fails to stamp the packages is 1 over 90. Next, the probability that Pat stamps 5% of the packages is 5%. Okay? Then the probability that Pat fails to stamp the packages is 1 over 200. Okay? So here, we will use the formula for Bayes' theorem. So, probability of John fails is equal to uh, the numerator will be John because uh, it is what is being asked in the study, in the problem, okay? So the probability that John stamps the package multiplied by the probability that John fails to stamp the package. All over, okay? So the probability that John or J multiply by the probability that John fails, okay? Plus the probability that T multiplied by probability that T fails, okay? Plus the probability of FR or Frank multiplied by the probability that Frank fails, plus the probability that Pat stumps times the probability that Pat fails to stump, okay? So whatever is being asked in the question, it is found in the numerator, okay? So substituting all the data that we got and simplifying, we get 12 over 107. So that is the answer.